Ladies and gentlemen, we are building up the foundations of thermodynamics, and you're going to have a solid understanding as you go through this journey with me. Today, we're going to cover something very important, and that is states and substances. And it's very important because we say the word state in like every second sentence. So here we go. We're going to describe substances, describe thermodynamic properties, and then get into states and equations of state. So we're going to start off with something that you likely already know from elementary school, and that is matter, which is anything with mass that takes up space. And a substance is matter with a constant composition. So the chemicals within it are just kind of hanging out and they're not changing over time. That's different than something like a chemical reaction that's actively proceeding, where that's not a substance because the chemical species are changing over time. Now, a substance can either be a pure substance, so one chemical within it, that's it, or a mixture of substances within it. And whether it's pure or a mixture, they can be homogeneous, so the substances are mixed uniformly throughout, or it can be heterogeneous, so not unequal mixing or of different phases. Now, I'll do a couple examples of them, and there's one box here that might surprise you. So, examples of pure substances that are homogeneous are things like liquid water, carbon dioxide gas, and even things where there's like a bunch of elements, but if it's a single chemical species, here this is magnesium sulfate hexahydrate, this is a pure substance because it's like one type of salt. Okay, so homogeneous mixtures are things like salt water, air, steel, anything where it's mixed all uniformly together. Now, this one gets a lot of people sometimes. There are pure substances that are heterogeneous, and those are pure substances in different phases, like ice and water. Or if you have like an iron bar and you melt one side of it, it's kind of liquidy, it's heterogeneous, some solid, some liquid. So even though it's a pure substance, it's all iron. So anything with multiple phases when it's a pure substance is heterogeneous. For mixtures, there's like a gazillion examples like oil and water, granite rock, smoothie, smoke. Smoke has colloids and things in it. So yeah, there we go. Now, properties, as we're building up, starting at the very fundamental things, properties and a very basic level describes some feature of the system. And properties can either be macroscopic, so those describe the system as a whole, so things like pressure, temperature, volume, things like that. Or they can be microscopic and describe the behavior of individual atoms and molecules. So like the velocities, kinetic energies, momentums of the specific molecules themselves. Now in the land of thermodynamics, we deal with the macroscopic world. However, we often use the microscopic world to help describe macroscopic behavior. Okay, properties can either be extensive or intensive, and this is extremely useful in thermodynamics. Extensive depends on the amount of substance. So if you have like a gold bar, you cut it in half. If the property changes, then it's extensive. So things like mass, each half now has half the mass, half the volume, and half the amount in moles. But extensive properties, they don't change on the amount of substance. So things like density, the density of the gold's not going to change. It's the same temperature and the same pressure. Now, the reason I said this is important is because to generalize our results in thermodynamics, we generally want to work with intensive properties. So if we have some extensive properties, and here I just got some random ones, volume, mass, and energy, if we divide it by the amount in moles, we turn it into an intensive property. So rather than the specific volume that we're working with in the lab, you divide it by the amount in substance, and then we know the volume for every given mole. The mass divided by moles is the molar mass, and then rather than the total absolute energy, we divide it by N, and that gives us the energy per mole of that substance. Density, it's a ratio of two extensive properties, and that's one way to get an intensive property, is we take a ratio of extensive properties. Okay. So a state, and this is super critical that you know what a state is because it's mentioned like all the time in thermodynamics. It's quite a simple concept. It's a collection of a system's properties. This is distinct from a phase, which is like solid, liquid, gas, plasma. Those are phases. A thermodynamic state describes the system by its state properties. So this system right here can be described by its pressure, volume, temperature, the mass, the moles, things like that. That set, that collection of properties is its state. The state describes this system or any system as it is when there's no energy being transferred. And that's super important. Okay, no energy is being transferred. The state of the system is a collection of its properties. Sometimes your prof might call these state variables, state properties. There are slight differences in here, but they're often used kind of interchangeably, which is mostly okay. Now, state equations, aka equations of state, are equations, math equations that relate state variables to other state variables. So here's an example. This is the most famous one of all. This is the ideal gas law, PV equals nRT. This is an equation of state. If we divide by V and solve for P equals nRT over V. Written this way, pressure is a function of the amount in moles, temperature, and volume. Okay? But all of these four variables, these are all state variables: pressure, moles, temperature, and volume, because they describe the state of the gas as it is, right? But written this way, when we're solved for pressure, pressure is a state function because it's a function. Its value is a function of these other state variables. Now, the only reason I'm picking on this is because your prof may interchange these words, state variables, state functions, state properties, to all mean the same thing. And for the most part, they are, but there are kind of slight differences. Okay. And that's different than path functions, which describe how we go from one state to another. And there's two main path functions. There's heat and work. So if we have two states right here, this is state 1 with pressure of 1 bar, volume of 5 liters, temperature of 25 degrees Celsius. Its state is described by its pressure, volume, and temperature. State 2 has half the bar, double the volume. Its state is also described by the values of the pressure, volume, and temperature. These are state properties that describe the state. Path functions describe how we go from state 1 to state 2. And we do that using either heat or work. So we can go from state 1, we can heat it up all the way to get to state 2, or we can apply some heat or do some work. So those are path functions. All right. Thanks for continuing with me on this journey, this foundational journey of thermodynamics. I really hope you have a solid understanding so that you don't go through it the way I did the first time with thermodynamics, like totally confused, not know what's going on. Having a strong base is just going to really set you up for the whole rest of the course. And I'm with you here. I'm with you every step of the way. See you in the next video, and good luck in thermodynamics. Cheers.